For 100 years, we've sensed the presence of an invisible force, dark matter, first proposed by Fritz Zwicky in the 1930s, and later confirmed beyond a reasonable doubt by Vera Rubin herself. What would the universe look like without dark matter? Galaxies would still form, but they'd fly apart. Their outer stars would spin off like sparks from a pinwheel. In 1933, Fritz Zwicky noticed this problem in galaxies within the Coma cluster. The visible matter couldn't account for the galaxy speeds he observed. He called it dunkle materie, dark matter. Decades later, Vera Rubin found the same mystery in spiral galaxies. Stars far from the center weren't slowing down. Rotation curves were flat, speeding up, an astronomical anomaly begging for an invisible explanation. Imagine two galaxies, one governed by Newton's laws alone, and one with an unseen halo of dark matter. In the dark matter-rich galaxy, stars at the outer edges orbit almost as swiftly as those near the center. This observation is a cornerstone of the dark matter hypothesis. It suggests not only that there's an unseen mass enveloping the galaxy, but that the dark matter would produce a telltale heartbeat, revealing its presence. This iron ball is heating to 3,000 degrees. As it glows, it's radiating light across the electromagnetic spectrum. We can see it, we can measure it, we can interact with it. This is normal matter, behaving exactly as we expect. It's dark and it's matter, but it's not dark matter. And most of the universe, it's nothing like this ball. Picture this. You're hunting for something that makes up 85% of the universe, but you've never seen it, can't touch it, and you aren't even sure you can prove that it exists. Your detector sits a mile underground, colder than Antarctica, waiting for a collision that might happen once in a decade. And when it finally does, you're not even sure it's real. That's exactly what happened to my guest today. And what he discovered next will completely change how you think about the invisible universe around us.
I knew this DAMA result since I was an undergrad student, right, in 1995. From experimental point of view, other experiment, almost all of these experiments that are more sensitive than DAMA have already excluded that particular signal.
Imagine Earth plowing through a cosmic headwind of invisible particles, dark matter particles. As our planet circles the sun, we glide on a helix, riding through that dark matter wind. Sometimes we push against it, sometimes it blows with us. In March, the Earth trails behind the sun. By June, it charges straight into the stream. The signal peaks. 6 months later, the Earth swings around, moves away, and the wind slackens. It's then when the signal dips. And then the pattern repeats, orbit after orbit, year after year. This annual rise and fall is the telltale heartbeat scientists have been searching for, the faint whisper of dark matter. And this signal is what the DAMA LIBRA experiment claims to have seen, not just for 1 or 2 years, but for nearly the past 30 years. The signal that piqued Kaixuan's interest 30 years ago was produced by the DAMA LIBRA experiment. It shows the telltale pulse of our cosmic dance around the sun as the sun itself moves around our galaxy. The predictions of the dark matter model match exactly on what DAMA LIBRA has observed. So why don't all of Kaixuan's colleagues agree that DAMA has made the definitive detection? Right here, on the campus of UC San Diego, scientists are working to see the invisible, the missing matter that makes up most of the matter in the universe. What they do is very complementary to what scientists using cosmic microwave background do. We're all on the same team, although it's claimed that scientists, competitors, have seen a dark matter signal for over 30 years. This signal remains controversial. We'll explore the nature of that signal, how it was made, how it was first detected, and why colleagues are very skeptical about it. We'll interview the primary players in the new generation of searches using liquid noble gases like xenon, and fighting against backgrounds, man-made, natural, and cosmic in nature. We'll reveal the techniques and technologies that spin off from this research, and in a fascinating way that this research into cosmology and particle physics may pay dividends in helping maintain peace, detect rogue nuclear weapons,
and even prevent a nuclear war. All this happens not far from UCSD's famous Urey home, named after Harold Urey. It's famous for many things. He was the first person to detect and measure the properties of deuterium, which plays an enormous role not only in particle physics, but in cosmology as well. The abundance of deuterium is one of the best pieces of evidence that we have that the Big Bang occurred. Its abundance ratio matches almost perfectly the expectations that one would get from an early universe which is extremely hot, extremely dense, a fiery furnace, fusing protons and neutrons. And that may seem implausible. How can a neutron, which is neutral, bind to a proton, which is positive? Well, that's what Harold Urey figured out, measuring heavy hydrogen, paving the way for the measurement of tritium, which is radioactively unstable. And we've named our building, the chemistry department, is named after her. Won the Nobel Prize for his discovery.
Before we dive into the controversy that's been tearing the physics community apart for 30 years, you need to understand what's at stake here. If the Italian experiment we're about to discuss is right, DAMA LIBRA, it's the discovery of the century. If they're wrong, it's the most persistent false signal in human history. And what makes this extraordinary? My friend, Professor Kaixuan Ni at UC San Diego, is about to tell us why he spent his entire career trying either to confirm or debunk a claim that inspired him as a 20-year-old kid back in 1995. That was 30 years ago, 3 decades, his whole life's obsession. And the signal, well, it's still dividing scientists to this very day. The universe would look very different without dark matter. Galaxies would spin much slower than they're observed to spin. The Earth, following the Sun, trails at a much faster rate than would be expected if there was no dark matter in our galaxy.
Can you explain what the current thinking is of this experimental results? They claim 20 sigma detection. They've measured it since 30 years now, and yet they're the only ones that believe it. So what is the state of perception of this result within your field? Is it a detection? Is it definitely not a detection, or somewhere between?
I knew this DAMA result since I was an undergrad student, right, 1995. And that probably triggered me to come to US to study dark matter. But still exists now the conflict with other experiments. And so from experimental point of view, almost all of these experiments that are more sensitive than DAMA have already excluded that particular signal. So they detect something, but something might not be dark matter. Might be some background that remain in their detector.
Can you explain the principle behind the annual modulation technique?
So annual modulation is really coming from like dark matter. Dark matter is in our galaxy, right? Also on the Earth. And the sun is moving around the galaxy, so it has a speed. So basically the sun has a relative motion with the dark matter halo, we call it. And the Earth is rotating around the sun, right? So in June, when the Earth is rotating in the same direction as the sun, the speed relative to the dark matter halo is larger than in December, when the Earth is rotating in the opposite direction of the sun. So that different speed making the event rate different in the detector in June and December. There could be a 5-10% of variations, as we call annual modulation.
So if we detect such an annual modulation with a lot of events, that could be a confirmation of dark matter signal. I say could be because there are other background could also modulate at the same pace, such as like cosmic ray muons interacting at the underground detector.
Those 3 experiments are all in the northern hemisphere. Is there a plan to build an identical copy of DAMA or something Kaixuan Ni in the southern hemisphere with the annual modulation?
Yeah, there are proposals trying to build, for example, I believe the SABRE experiment in the in Australia, the southern hemisphere, could make the modulation maybe the phase different compared to the other hemisphere. But that experiment is still, under building. Yeah.
Hold on to what you've just heard about seasonal modulation, because in a minute, Professor Ni is going to reveal the technology that makes his detectors fundamentally different from the controversial Italian experiment called DAMA LIBRA. What he's about to describe sounds like science fiction. A chamber that can fingerprint individual particle collisions at the atomic level? It's like CSI particle physics. And that fingerprinting capability, it's exactly why the physics community is so divided about the 30-year-old claim of success by the DAMA LIBRA experiment. No other event in scientific history has lasted so long without confirmation and yet been accepted by so many as being truth.
Can you explain the way that xenon detector system, your experiment, works? What is a dual-phase time projection chamber, TPC?
So we use a dual-phase, we call dual-phase time projection chamber. Is mainly a liquid phase is the main target for interacting with the dark matter. And above that is a gas phase. And we need a gas phase because we want to amplify the signals. The dark matter detects very low energy signal in the liquid xenon and then produce ionization. And this ionization had to be drifted into the gas phase. So any tiny sub-keV events can be amplified. One electron can be amplified by 100 times, 1,000 times, turn into light, and then we can detect these tiny energies. That's the main, advantage of dual phase.
Yeah, time projection sounds very futuristic. What does it actually mean, time projection in chamber, TPC?
So it's first, we have one interaction, and then the ionization start to drift, right? So there's a time. So you know the time, and this time tells you the event position in this direction. So that's where the time comes. And projection, sometimes you can also think of as, in our case, this event eventually will be ionization charge will be drifted on the top, and it will give you localized the signal. And this localized give you the kind of a position in this direct XY direction. So that gives you kind of projection.
Okay. And so it's very different than the DAMA experiment. The DAMA uses scintillation. Dark matter, if it exists, comes in, and there's a reaction that causes a pulse of light, effectively, correct?
That's right. DAMA uses the scintillation. We also use scintillation. Before the ionization charge drift, we also have a direct scintillation, but we have two signals. So these two signals will tell you actually the difference between main background from the actual signal. DAMA, I believe, is just using the scintillation. Because the crystal is actually a scintillation crystal. Their scintillation crystal is also very pure, very clean. And they detect these scintillation pulses and trying to look for them into whether, or they cannot tell the difference between a nuclear recoil or electron recoils or backgrounds, but they can just count how many events to the lowest energy possible, and then use the modulation as information.
I see. So it has less
Discriminating.
Yes.
Yeah.
I want to pause here and give you some perspective on what we're talking about. The interaction Professor Ni just described, a dark matter particle hitting a xenon atom, would be like a mosquito flying into a freight train and somehow leaving a trace in the freight train's trajectory that we could still measure. The precision required is almost supernatural. And yet he and his colleagues, team, and friend, including past guest Elena April, have built machines that can do exactly that. So if they're so good, if they're so sensitive, why can't they confirm a signal that's been reported since Bill Clinton was president?
So we mentioned some of the concerns about the DAMA results or reproducibility and confirmation. Why has it been so hard for other researchers to confirm or refute the DAMA LIBRA results?
I think one thing, the mental point is you need to get very clean crystals, very pure crystals. If your crystal is has some radioactive contaminants that continues emitting background, then basically you cannot see as clean as DAMA can see. The technology actually accompanying maybe it's not open to the public. So other people who want to use the same type of crystals For example, I believe Princeton University actually grow their own crystals for the SABRE experiment.
So if you were to meet a hypothetical student who is interested in working on DAMA for their PhD, how would you advise them? What would you say to them?
Oh, working on DAMA or working on SABRE, for example, a confirmation experiment.
First DAMA, yeah.
I would advise students to say, look into the data, really understand the background at the lowest energy possible, and see if there's any systematic or other background that we haven't found or the collaboration hasn't found, to see that can also produce a modulation signal. That could be, a very large contribution to the community if you student want to work on the DAMA experiment.
How does Xenon's, your project, how does it handle sharing data, making data public or accessible to the community? Does it, or does it keep it proprietary?
So, the data we take, he mentioned that petabytes of data is, the initial data is very, not noisy and full of, contamination. You have to understand or detect in order to use that data. So even that give to a public, it's difficult to use. But we do all kinds of data selection, cuts, and eventually produce, these selected events, and that we use them to produce so-called limits, so we don't find dark matter. And these data, once we publish our paper, we describe all the method, and these data are also attached to these papers, making them public. So people, for example, want to check our signal, check our signal detecting efficiency, you can look at these data. If they want to use them to constrain other type of dark matter models, they can also use this data. And if people are interested in, more experimental part of our background, then I would, welcome to join our collaboration. Yeah.
Here's where the story takes an unexpected turn that, quite frankly, keeps physicists up at night. While hunting for dark matter, Professor Ni's team stumbled upon something they never intended to find. Particles streaming from the core of our sun, passing through your body right now, completely undetected. They filtered petabytes of data. They used machine learning and AI to identify patterns and found exactly 11 events out of millions of possibilities. The amount of haystack that needs to be thrown out to find that one needle is truly extraordinary. This is detective work at the level of individual atoms, and what they've discovered makes finding dark matter, unfortunately, even harder.
What is the most significant source of contamination or systematic effects, both in the laboratory and in the cosmos, astrophysical systematics and terrestrial systematics?
I think mostly background, right? I mentioned, the backgrounds coming from all kinds of sources, from detector material and from astrophysical source like neutrinos. So in our current generation experiment, the most backgrounds coming from detector material, say radon in the xenon, and it depends on what type of a signal you're looking for. But for our next generation experiment, solar neutrino will become one of the dominant background.
You mentioned there was a recent detection and publication, in fact, I think, about the solar neutrino detector properties of xenon. Can you explain that result?
So the sun produced abundant neutrinos, right? And from the PP fusion, and there's a reaction chains. So they are producing different kind of neutrinos. We call them PP neutrino, we call them boron-8 neutrinos, and different energy, different spectrums. And last year, the paper we actually released is about observing about 12, 11 neutrinos from so-called boron-8 neutrinos. And these neutrinos produce a nuclear recoil in our detector, very low energy nuclear, like about keV, and very difficult to detect. And we managed to do all kind of analysis technique, including machine learning, trying to filter out all the noises, and eventually found 11 these kind of events out of total 37 events we detected another 26 are backgrounds. And these are the results we call it first detection of solar neutrinos in the liquid xenon detector. And that makes our experiment in the future will be more difficult to observe dark matter around 6 GeV, which produce the same type of spectrum as the boron 8 solar neutrinos in our detector.
Okay. Speaking of precision, Professor Ni is about to tell us about witnessing something that happens so rarely, it makes winning every single lottery on Earth look like the odds of Manny Machado hitting a home run. We're talking about nuclear decay. Nuclear decay with a half-life, probability of reduction by half, longer than the age of the universe. And Professor Ni and his team, well, they caught that happening multiple times. So if they can detect something with this impossible rarity, why does dark matter mystery elude them?
About 3 years ago, when you were first on my podcast during COVID, 4 years ago, maybe 5 years ago, I forget.
Oh yeah, I remember that.
It was a detection of a very rare decay, or some very rare nuclear process. Can you explain that and what the latest findings are from your research on that? Strontium, maybe?
Yeah, I remember. So there was several observations in the past 5-6 years. One is so-called double electron capture of a xenon 124 element in our detector. And that's a very rare decay. Electron capture is very often, but double electron capture, having 2 electron capture at the same time, it's very rare. The half-life of that process is 10 to the 22 years. It's very long. That's probably the longest half-life direct decay that we detect directly in a detector. And at that time, I think we observed about 3-4 sigma, and then later, we create more data. Now it's 5, 6, even more than that. Other experiments like PANA-X and I believe ALZ also see the signals later. And this is just standard model process, just very difficult to detect. That's the double electron capture we observe. But I think one thing that we actually talked about is some excess signal coming from our very low energy electron recall from a xenon 1-ton experiment.
Yeah.
So at the time, actually a grad student from UCSD, Kim Chang-Yi, he's a professor. He and another student from Chicago, they found some excess signals in our electron recall, not nuclear recall, electron recall background. And trying to expand with all kind of background we know, and there's still the excess, And eventually we think maybe these could be some background we don't know, we didn't count into. For example, tritium. That's weak. But, that tritium amount must be very low. We couldn't detect them. So that's one possibility. But there could be also more exotic explanation. Say, the neutrinos may have a magnetic moment. A solar neutrino may have a magnetic moment that can produce a higher rate than we expected, or maybe solar axion. So that's the paper we wrote and trying to explain excess. We didn't have any conclusion, but that's some possibility for the excess.
What you're about to hear is why I love experimental physics. Professor Ni's team thought they may have detected something exotic, possibly solar axions or neutrinos with magnetic moments, the kind of discovery that would rewrite textbooks. But then they had to build a cleaner detector, and unfortunately for them, their signal, their possible Nobel Prize, well, it disappeared, perhaps for the time being only. But honestly, this is how good science works. It's exactly the kind of story that I love to tell, and that makes the 30-year DAMA LIBRA controversy so frustrating, but also so energizing.
So later, after during the COVID, we assembled a xenon N-ton experiment. It was larger, cleaner. We made a lot of effort trying to remove, to heat the detector before we actually feed xenon, trying to remove this kind of tritium, if there is anything exists, right? And then when we start taking data and much lower background, the excess is gone, right? We didn't find any excess. So that means, the explanation of tritium could be the right explanation, not solar axion or solar neutrino magnetic moment. So that's like a kind of a, I think, for example, we mentioned about DAMA, right? If there's excess, you could explain with dark matter, but there could also be background. And in trying to do more experiment, trying to prove or refute such hypothesis. And that's what we did from xenon 1 ton to xenon n ton. We claim a signal, and now we are looking, for example, when we detect, collect more data, continue to looking for solar neutrinos.
How can a neutrino, which is neutral, have a magnetic moment?
Well, in the standard model, a neutrino may not have a magnetic moment, or very low, tiny, that we would never see. But there are some exotic theories beyond the standard model that has a larger magnetic moment. That's physicists are trying to see. If we see such kind of a large magnetic moment, that could be something new.
And how does it compare to like Zeppelin and Lux and the other double beta decay, neutrinoless double beta decay, which look for the electron spectrum?
Right, there are different isotopes, and for people using liquid xenon, that's the xenon 136, like Nexo collaboration, LZ collaboration. They all have this xenon 136 elements, and even dedicated, for example, CamLan-Zen. And but for LZ and the xenon n ton, the element xenon 136 now detects not enough to get the same sensitivity as the dedicated double beta decay experiment. So, but in the future, xenon and LZ, and also the Darwin collaboration in Europe, we joined together to build a so-called next generation XLZD experiment that eventually contains 60 to 80 ton of liquid xenon, natural liquid xenon, and that will contain about 6 to 8 ton of xenon 136 element. That will push the neutrinos with double beta decay half-life xenon to up to limit about 10 to the 27, 10 to the 28 years.
Wow.
And there will be a very sensitive experiment in that process as well. So, Dr. Brian Keating.
Hello.
These are the students, Bao, Xinyan, and Dachen. They are three from Columbia University.
Okay, well.
Yeah, they are senior graduate students working on the xenon. Yeah, and you is my student.
Oh, really?
Yeah. For future detectors. And in the our dark matter search experiment, xenon is located in the underground lab in Italy, Gran Sasso underground in Italy, and it's a huge tank full of liquid xenon. Total about 6 tons of liquid xenon in the target, waiting for dark matter interactions. But here you see it's very tiny detector, right? So, but very similar. We have a cryogenic system, we have purification system, we have data acquisition system. And here is a little detector we're trying to build for, for different applications.
Is that like a prototype or is that hype? Okay.
It's
also for dark matter, for neutrinos or some other.
We want to use it for detecting reactor neutrinos. The neutrino can also interact with the detector, producing signal very similar to dark matter would produce. So we're trying to use the same principle of detector, but reactor neutrinos are very low energy and produce nuclear coil, very low energy nuclear coil, very difficult to detect. Yeah. So I have another setup downstairs in a high bay, which is slightly bigger than this, that will eventually be built as a reactor neutrino detector. So you could find our xenon. The xenon is contained in these high pressure bottles, and because they are expensive, so we don't want to lose time. And usually contains bottles, and we have about 10 kilograms in the lab right now.
So I'm Zhao from Columbia University. Currently, I'm working on the xenon experiment, which is so I'm working on the xenon experiment, which is a dark matter direct detection experiment. It's located deep underground at LNGS in Italy. So our experiment has a lot of subsystems, but the core of the system is a so-called dual-phase liquid xenon temperature chamber, or the TPC. So, when a particle gets scattered inside the TPC, with the xenon atom, it can generate both scintillations and ionizations. So the scintillations or the prompt scintillations can be detected by the top and bottom PMT arrays. In this system, is silicon PM. The prompt scintillation can be detected as a so-called S1. And we also have applied the drift field, so the ionized electrons will drift upwards and reach to the liquid-gas interface, and finally be detected as S2. So from S1, S2, we know quite a lot of information. Like we can reconstruct the event's positions. We know the energy by the S1, S2, but most important, as Professor Kaixuan just said, we need to discriminate our signals from the background. And in the WIMP search, the dominant background is from the beta decays or the gamma from the materials. So these background events are so-called nuclear electronic recall events. And because WIMP is expected to be electronic neutral, so it should be expected to be nuclear recall events. So the key of the xenon anton experiment is to discriminate electronic recall events from the nuclear recall events. And for these two different types of events, or the recoils, their S1, S2 ratio are different. And this brings a lot of power to discriminate the signals from the background.
In S1 and S2, that's self-interaction. What can you explain what S1 and S2 mean in this context?
Yes. So the S1, S2 mainly means, so in our analysis, it mainly means the size of the pulse. So, the S1 and S2 are both scintillations, but the S2 scintillation is from the proportional, from the drifted electrons, and it's proportional to the number of electrons. But anyways, these are both photons and be detected by the PMTs, and you have the waveforms from the PMTs. So in our analysis, the S1, S2 usually means the size or the integrated area of these pulses.
For example, our primary goal is to observe the WIMP dark matter, and their signal is large, relatively large than the neutrino interactions. And without this triggerless system, we might not be able to observe those very low energy signals, or the S2 only analysis or S1 only analysis without this triggerless EQ.
You can just take a look at here. I mentioned this is so-called radon reduced clean room that would be for building the next generation experiment. So as I mentioned, radon is one of the dominant background for us, and for any low background dark matter or neutrino experiment. And the radons continue emanating from the materials, right? And so we want to make sure all the material put into our detector is very much controlled in terms of radon emanation. So this especially build clean room, and you see inside the all metal coated, and make sure and even the air, even in our normal air, there are radons, right? So we have special radon removal system. If you want to take a picture here, this we inherited from an experiment called the XO200, neutrinoless double beta decay experiment that's measure Majorana particles. And so this system now is retired, and we use it to clean the air here, and then pump the radon, remove the air into the clean. Yeah. So this is Professor Liang Yang's lab.
Okay. Yeah, give me a quick tour. I know.
And we'll see you around. Yeah.
I'll get him next time.
Yeah. This he's building some electronic readout.
Sometimes you can beat swords into plowshares. We're about to see how the search for cosmic mysteries leads to very earthly applications, benefits, and truly hope for us to wage peace. The Pentagon looked at this dark matter detection technology and saw something else entirely, a way to monitor nuclear reactors from a distance, to verify treaty compliance without ever setting foot inside a facility. This is how basic research, fundamental research, can pay unexpected dividends. It's what happened in my field, the cosmic microwave background. We're building sensitive detectors to explore the wispy radiation from the Big Bang, eventually led to advancements in cell phone communications technology. Professor Ni's project is funded by DARPA, the same agency that gave us the internet. We all know what a benefit that's been. This has a different type of benefit, one perhaps to help us seek peaceful resolutions to potential nuclear conflict.
This is the apparatus actually we are building, and we call it neutrino detection with xenon. And we know the xenon detector now detect the solar neutrinos, right? We want to use this detector technology for some application. For example, detecting neutrino from reactors. We can monitor the reactor field, remotely, not very far, 10, 20 meters away. And the detector is set up like here. Let me just open this. So the principle is very much the same as a dark matter detector. You build a cryogenic system, you have a detector vessel, and you have calibrations and trying to purify the xenon, more or less the same. Just eventually you want to contain less than 100 kilograms xenon here, place it very close to a reactor core. And then we start to see a lot of reacting signals.
Could you use this for like weapons detection or trees violation of nuclear, proliferation, things like that?
That's the main purpose. Like you want to measure the component field in the nuclear reactors. Not from using neutrinos, and to see the compositions, making sure the component inside is not changed during some down period. Yeah, that's the eventual goal.
So is this funded by DOE or?
It's a DARPA program. Yeah, but I had a 3-year program, and we built this setup for
So can I cut through?
Yeah.
So there's 100 liters, you said?
Eventually, like 100 kilogram, we usually say kilogram mass. Yeah, and more or less this system is we built based on the dark matter detector technology. Yeah, and
so what is this his thesis or later?
no, he's from Columbia. He's a visiting student. Yeah, this is actually my former student postdoc helping to build this system, and he already left. Got a professor position somewhere else, and now students are working using this setup actually to build something useful for neutrinos.
Wow, there you go.
Yeah.
Yeah, very nice.
Here's what we've learned today. For 30 years, one experiment has claimed to detect dark matter. For 30 years, increasingly sophisticated detectors have failed to confirm the DAMA LIBRA claim. We've seen technology so precise it can catch neutrinos from the sun and witness rare nuclear decays that on average take longer than the age of our universe. But dark matter itself, well, it's still invisible, still undetected, still undefeated, still the greatest mystery in modern cosmology. 85% of the universe is missing or made of something we've never seen. That should be humbling, but it should also thrill you, because if most of reality is still hidden, imagine what else we can discover. If you want to see this technology in action in detail, check out the documentary on Professor Keating Experiments channel. Links in the description, or click here. The search for dark matter isn't just about finding particles, it's about building the tools that reveal the invisible architecture of reality itself. And that search, well, my friends, that's just beginning.